Thanks for inviting me again, and my apologies for not being able to come over this week. So 2 weeks ago, I gave a bit like of a more technical talk about some of the things we do around specification WebAssembly. And in this talk, I'll try to set a bit more like context about WebAssembly in general and why we think it's important that it's like formally specified and all. So for those who were not here like 2 weeks ago, just a quick recap of what WebAssembly is or how you should best think about it. So WebAssembly, also known as WASM, essentially in a nutshell, it's a low-level virtual machine. And virtual machine in the sense that the Java virtual machine is a virtual machine, so more like a language runtime, not like a process virtual machine. And it's low level, which is what it distinguishes it from other virtual machines in that space, is in the sense that it's really a thin abstraction, or tries to be a thin abstraction over actual CPU instruction sets. So as thin as we can make it, essentially. So it's really abstracting the hardware, not some specific programming language. And it tends to be safe, portable, and predictable in terms of performance and semantics, and a bunch of other properties that I don't list here, but those are the ones that are probably most important in the context of what we are talking about. So yeah, essentially WebAssembly is abstracting the hardware, and that makes it a compilation target for languages, right? So in the first round of client languages, we primarily had low-level ones like Rust and C++. We also saw fairly early on a bit more high-level ones like Go and more high-level C#. But we're now seeing way more languages in the current round of kind of adoption. More modern ones like Scala, functional languages like OCaml and Haskell, Java as well. And of course, there are also people who can't learn from their mistakes and try to run JavaScript on WebAssembly, or things like Python for that matter. But basically all like major languages at this point can target WebAssembly in one way or the other. And they are like at different stages of maturity in that regard, but you can all run them. And the idea is when you can feed them, when you can compile to WebAssembly, then you can run them on all like contemporary hardware, more or less. So that's obviously the big ones like Intel and ARM, but also more at this time, I guess more exotic ones like say Motorola 68K or MIPS or PowerPC, and of course RISC-V as well would also be a valuable target. And most of these targets are already implemented for some of the engines. And yeah, and I should mention there are probably more than 24 implementations of WebAssembly itself now, also of varying quality and varying maturity, but there are several big ones, right? Especially in all the web browsers, but also a couple of off the web. And yeah, and some of these older processors, they are actually used in embedded space quite, so that's a space where WebAssembly is also important. So, but as the name suggests, WebAssembly runs on the web, and it's actually used by quite a few major websites these days. So they all run WebAssembly because they have to do compute-intensive stuff in some form or the other. And so WebAssembly has been an enabler for running these as web applications. So it's important on the web, but to be honest with you, the web, well, for the folks of us that kind of created WebAssembly, the web was really just an excuse. We were not all that interested in the web specifically. What we really wanted to build was kind of like a universal platform, a universal code format or virtual machine. That was not something we could sell to management at the time, thus the name WebAssembly, but that was what we like secretly had in mind. So in all its design and the way it's specified, WebAssembly is actually not a web technology. And that might be surprising to many. And whenever I tell that to somebody, they tend to be surprised. And But that is fully intentional. So WebAssembly is running on the web, of course, but it's also running everywhere else nowadays in all sorts of ecosystems like cloud and edge computing, mobile. It's running on various blockchains. It's running in embedded space, and people run it on desktop as well. So why is that? Why is it interesting to run WebAssembly elsewhere? So as I said, what we try to do is create a universal code format with the properties I mentioned earlier of it being like safe and portable and predictable. And that's what makes it interesting. So I'll give you a bunch of examples of companies using it. So one big one is, or like that has really fully embraced WebAssembly. It's one of the first ones with Fastly. So if, in case you don't know Fastly, Fastly is one of the largest content delivery networks, and many major websites are like feeded by some Fastly infrastructure. And that performs sort of edge computing for deploying stuff, and all the stuff that it's deployed and runs client side is in the form of WebAssembly modules. And they do that because it's a fast and safe way for them to do containers, software containers, essentially. Similarly, Cloudflare is another relatively well-known service that runs quite a substantial part of the web infrastructure, and they also use WebAssembly essentially to do sandboxing in a cheap manner. And then there are like container frameworks like Docker and Kubernetes that also interface to WebAssembly nowadays because it gives them a way to do lightweight containerization and because it's a portable container format. And prominently, like Solomon Hykes, one of the co-founders of Docker, is on record saying that if WebAssembly had existed in 2008, they would not have created Docker. So because it's kind of like providing similar abilities in a more portable manner, in a simpler manner. The Cloud Native initiative is also embracing WebAssembly to do server-side run client code server-side in a safe manner. So again, like this form of isolation. There's the Bytecode Alliance that was formed specifically to support WebAssembly as a portable platform. And then there are blockchains, and there are quite a few. I just show one here because I'm more familiar with that one. And they run WebAssembly as basically their compute format, right? So these are blockchains where you can run arbitrary code in the cloud essentially as well, but in a replicated manner. And the format of this code is WebAssembly. And one particular reason why they care about WebAssembly is because WebAssembly provides deterministic execution semantics, which is of course necessary if you depend on consensus for replicated computation. Another important use case nowadays are embedded systems. And for quite a while, I was really like puzzled, why would you run WebAssembly in embedded space where you really need to be close to the hardware and everything? And we knew that various companies like Siemens, I'm just naming one here again, are doing that. But we didn't quite understand why, but more recently, because most of them, they don't really like to talk about it, but more recently they told us why they care, and it's basically portability. So in embedded space, you're dealing with lots of diverse like CPUs, hardware parts that change all the time, and was like really expensive and annoying for them having to redo their entire tool chains all the time, right? So what WebAssembly provides to them is basically the ability to just have one tool chain and then really just swap out the backend in a way. Another use case is also interesting in the context of what we discussed here. So Firefox has been using WebAssembly as a means for isolating unsafe legacy code. So they needed to, at some point, integrate some font scaling or rendering engine, and they had some legacy C code doing that lying around, but they didn't trust it, right? For obvious reasons. I don't have to convince you. And what they did was something very simple. They just compiled that C code into WebAssembly and then ran it in the WASM sandbox. And that solved all their problems. So this is an interesting use case because I totally agree with what Robert said yesterday, right? It's not necessarily realistic that all this legacy code that's out there on unsafe languages, we that will be ported to something safer anytime soon. Unfortunately, I also think it's equally unrealistic that we will port all the hardware to something safe, like with Sherry or something. So WebAssembly is kind of like a very cheap solution for isolating your unsafe legacy code in the meantime. And finally, because these days it seems like you can't give a talk without at least mentioning AI, there's some research project at Microsoft that are now putting it into AI in an interesting way. So they have this AI control interface, which is used to control like beam search, so basically the pruning in queries to a large language model, and to make that configurable in a way that programmers can kind of control it in any language they want. They use WebAssembly as the format in which these algorithms for tuning or the controlling this are shipped to the server that serves the query. So, and that is, yeah, one use case there is that it's language neutral and you can use different languages to do this control. So yeah, there are various different reasons why people use WebAssembly in these spaces, and both client side, server side. It often has to do with containerization and sandboxing and isolation and portability, right? So, and of course, all these use cases are particularly relevant, make it particularly relevant that it's a well-defined thing. So that's why we care specifically about having a good semantics and a formalization in particular. And of course, to start with, a good design, right? So I want to walk through a couple of points which are like essential points that make WebAssembly safer than probably other like comparable technologies or languages in general. Some of them are shared with others, some might be not. So first of all, WebAssembly is, as I said, it's a virtual machine, but it's not like a traditional von Neumann machine. It's actually a Harvard machine, meaning that code and data are strictly separated, right? So there's no way to get the address of some code or manipulate it or read it in any way. And I mean, this is common in virtual machines, but it's important to emphasize because, of course, it rules out a whole range of attacks. And at the same time, we can still compile something like C really efficiently to it. A closely related thing is that what is called a trusted call stack. So again, like the stack, the traditional stack is not exposed to programs. You cannot take the address of anything on the stack. There are no pointers into the stack. You cannot get to return addresses. None of that is exposed. When you actually access proper memory, like data in memory, then in WebAssembly being low level, this is really just a huge byte array, right? Or several of them. So you just index into a byte array, but that is of course bounds checked. And there's no way to access any memory that you haven't actually allocated yourself. So that means, in that sense, WebAssembly is memory safe, but of course, this is a bit of a more nuanced way of talking about memory safety. It's memory safe on the level of WebAssembly, right? But of course, that doesn't necessarily imply that any like language running on top of it is memory safe in its own memory model. So when you compile C to it, that can of course still smash its own data by doing stupid things, but it like can never affect any other module or code. It cannot escape its sandbox like you would expect. Somewhat maybe less or less common thing in VMs or low-level code formats in general is that WebAssembly also has structured control flow. So there are no arbitrary jumps, and jumps address labels in a syntactic fashion, not by byte offsets, in the binary format like the JVM would do, for example. And that by construction basically gives you control flow integrity. There's no way to mess with the control flow. So these are like more concrete things. Then there are more like various properties it has. So WebAssembly is typed. The type system is fairly simple because it's low level, but still like all instructions are type checked through a process we call validation. So similar to bytecode verification in the JVM, but actually specified as a proper type system. And then there's the real big one, which sets it apart, I think, from all other low-level languages, code formats, and all these things. So WebAssembly has absolutely no undefined behavior. Everything is fully defined. There are no loopholes whatsoever in the semantics. And this extends to even to things like the relaxed memory model. So WebAssembly in the coming version has threads with a relaxed memory model because we're exposing the hardware essentially. But unlike almost all languages with relaxed memory models, they heavily rely on undefined behavior. We don't. There's nothing. Everything is well defined. It may be non-deterministic in various ways, but it's always well defined. And then the thing that makes WebAssembly important for things like sandboxing, containerization. So every WebAssembly binary is essentially a module that can have imports and exports. And these modules are fully encapsulated. And then the code inside such a module cannot do anything by itself other than just compute. So it can heat up your CPU, but that's all it can do. It cannot access the external environment at all unless it's explicitly given the capability to do so by supplying some of its imports. And the client of the module is in complete control over what it supplies to it. So essentially, you're whitelisting like the capabilities this code has. You're not like blacklisting or access checking it after the fact. So it's a much safer approach for security, obviously. And another important thing is that the semantics is not just well defined, it's also where we could get away with it almost everywhere, deterministic. There are some pieces where we kind of were screwed over by dependencies we had, like the IEEE floating point standard not specifying what nans are. But in all other places, and hardware not agreeing, but in all other places, we try to really pin everything down to the last bit. That is important for portability, but also, of course, for safety because it makes the semantics simpler and more reliable, more predictable. And then maybe a profane thing that is often overlooked, WebAssembly has a simple semantics. Um, and this is also important. Like we talked about memory safety quite a bit in these 2 days. And memory safety is all great and fine, but there's some nuance to that. So I spent many years of my life working on a JavaScript engine. And JavaScript is a safe, memory safe language on paper, right? But it's also a language that has such a horribly complicated semantics that underneath in the implementation, you basically have no hope of ever making all that like free of errors and safe. All the security around JavaScript essentially is security by obscurity. These engines are like, if you think you know how complicated JavaScript engines are, then just add another order of magnitude, and then you might actually be there where it truly is. And similar arguments would probably apply to something like Python if we ever try to make it as fast as WebAssembly. So I think complicated dynamic languages are also a problem. So WebAssembly being a very thin abstraction layer is, of course, gives it the luxury of being simple in that regard. Like the lowering to the CPU is extremely simple and has some hope of being verified. But the biggest part, of course, and why I'm talking here is WebAssembly is formalized, right? It has a formal semantics. And this semantics is not just like an afterthought, it was actually an inherent part of the design process of the language from the get-go. And on top of that, we did not just write out the semantics on paper and did some paper proofs. There's also a whole mechanization. There are actually two mechanizations of the WebAssembly execution semantics and type systems with machine verified proofs of syntactic type soundness. So that was work done primarily by Konrad Watt and Philipper's group in the WASM CERT project, but we are kind of heavily leaning on them. And this mechanization and the machine verified proof was done before WebAssembly was officially published, or released is the better term here. So that is a really important bit here. So let me say a few more words about the WebAssembly formalization. A couple of these I already talked about 2 weeks ago. So I already said that it's an inherent part of the design process. But on top of that, it's also a normative part of the standard, right? It's not just something we do on the side. It's the whole standards document contains this semantics and is defined by it. And finally, going beyond what many other formalizations do, it's really end-to-end, like starting from decoding the binary format to really nailing down the last bit of your floating point operations or something that you can observe. So for programming language person like me, this is really like a big leap. Like the prior art of programming or prior practice of programming language specification was basically, from my perspective, stuck in the 1960s, right? Or maybe 70s, depending on how you view it. So in a way, I would argue we made a big leap here, like several decades, actually formalizing it, putting this formalization in the standard and doing it from the get-go. And I can, of course, assure you that this was not an easy thing to do. There was quite a bit of blood on the floor and people resisting it. And it continues to be some struggle occasionally, but we managed. At the same time, we're still far away from a future where you could like just formalize a language and that's your standard, right? The standard needs to be accessible to people, and most people, even like experienced engineers and compiler engineers, are unfortunately not educated to read even the simplest formal methods formulation. So for accessibility, the standard also has to contain like equivalent English prose. So it has this redundancy that it has both a formalization and a process specification. So yeah, success. But like, yeah, resonating Peter's question from yesterday, can we declare victory and move on? Obviously not, otherwise I wouldn't be here or asking that question. So to say why, let me briefly say a little bit about how the standard process works in WebAssembly. So WebAssembly is an open standard, non-proprietary, that operates under the roof of the W3C. And all the discussions and developments are completely public, mostly on GitHub. We have online meetings weekly, several ones actually, and they're also completely open. You can just register and show up. And when you show up, you also even get like voting rights immediately, right? So anybody can just show up and cast a vote on things that are on polls that happen. And this is maybe a slightly dangerous process, but overall it has worked sufficiently well for us. And part of the reason it has is that we have quite an elaborate process for doing proposals. So proposals is how we evolve the language. And there's a process for that that goes through various phases, which I won't explain in detail here, but there are like 5 phases with various deliverables. And each progression to the next phase requires a vote from the group, right? So that checks that all these requirements are met. And when you've reached stage 5, essentially, that's when your new feature is standardized. And like the first 4 stages here are like what the responsibility of the so-called proposal champion. So that's the person driving a given proposal. And the last step then has to be done by the specification editor. So currently that's me, essentially. So all this is the process, but then we also have this other thing going on, which is mechanization. And that's unfortunately not part of the proposal process. That's not something we can afford to do yet, right? Maybe in 20 years, that's something we could do. But right now, we already, as I said, did quite a leap by requiring a formalization. So as you can see here in phase 4, formalization is actually one of the required deliverables. So the mechanization is done not by the group, but by some academic researchers like Conrad, right, or Rao. So they have to do all the work, and they're not getting specifically paid for that. So that's part of the problem. The other problem here is that there are actually quite a few deliverables here, and they are all sorts of define like equivalent definitions of the same thing, like the language semantics essentially. But for various reasons, we require all of them, like both prose and formalization, as I said earlier. So there's a lot of work that has to be done. So this is a challenge, obviously, right? And it's a challenge because like WebAssembly development isn't finished, right? There are like more than 40 proposals in the pipeline right now, ranging from really small, like just a couple of instructions, to really cross-cutting things. And for all of these, you have to deliver all these spec artifacts, or extend all the artifacts right now. And we have to review them all and sometimes refactor. And after that, these volunteer academics have to pick up the pieces and keep up with the mechanization. And again, which is something they do as a volunteer work or just to further their academic career, but it's not something you can easily get papers out. So there are lots of bottlenecks here, a lot of work and bottlenecks. So questions like human resources, time resources, and latency, like if all this process takes too long, then that would be a problem. With like many people contributing ultimately to the specification, how do we ensure that it's all coherent and correct? And then there's the bus factor. Not sure everybody in the room knows what that is, but in industry, it's kind of like a cynical way to say like how much essential personnel there is. Like, so the number of people that can get run over by a bus without killing the project. So, and in the case of the WebAssembly formalization, this number is probably below 2, maybe close to 1 in some dimensions. And of course, there's the usual problem with funding. So to at least like address this problem to some extent, one project we recently started is we realized we need better tooling, right? We need tooling for keeping this up. And the thing we are working on right now is essentially a DSL named SpecTech for authoring the specification. And that's what I talked about 2 weeks ago, so I won't go through all of that here, but the basic idea is that we have a single source of truth from which all these artifacts can be generated, and this source of truth is a formalization. And from this, we generate everything, including the English prose. So the overall picture is something like this. We have the source that specifies the language, and then we can generate all these artifacts. And for example, here on the left, you have everything that makes up the actual official specification document in the end. And on the right, you have mechanizations and things like potentially auto-generating tests. So the dotted lines are things we are not working on yet, but intend to do in the future. We can also actually basically produce an interpreter from that specification, so make it executable in a way. And when we feed that the official test suite of WebAssembly, we completely pass that. And that gives us like quite a high level of assurance that the actual spec document is correct, right? Because it comes from the same source. And similarly, once we have ported all the proofs over to the mechanization generated for the COC as a COC theory, then we also know that all the formalism in the specification is actually correct. So this gives us a higher level of assurance than what we had before. So not just saving work, it also gives us a higher level of assurance, and probably a higher level of assurance than any other programming language specification ever had. And that was quite important to us. Yeah, so this is quite a big project involving several research institutes from Korea and England and Singapore and Scotland, and too many names to name them all here, like many PhD students involved as well. But yeah, it's a research collaboration, right? But it's one that actually already got approval from the actual WASM working or community group to adopt it as the future tool chain for the spec. So in production, in air quotes. But of course, it's still work in progress, and there are many things where we expect to still iterate on because we're operating in a space that is not well treaded, right? Where we don't really know what the right solutions are all the time. We're also experimenting with applying this to other languages because we believe there's quite a bit of potential here. So for example, there's some experiment with applying it, like specifying P4 with something like SpecTech. Well, of course, that doesn't solve all the things. There are still various challenges around the DSL itself, like how to keep its implementation robust when it's all just based on PhD students implementing it. There might be tricky features down the road, and the different backends might have different paces in terms of how fast they can catch up with the language evolution, and so on and so forth. There might be competing requirements. And of course, we still have all these other like meta problems of resources and who owns that thing, right? This is a research project, but we don't want to do it forever, obviously. So at some point, we would have to transfer ownership to the group, but is the WASM group, but is that group ready to take that? Does it have the relevant expertise? And how do we organize the knowledge transfer? All of these are completely open questions at this point still. Yeah, so I'm running out of time, so I should sum up. So WebAssembly has really embraced formal methods at this point, which I think is good, but that doesn't mean that all the problems are solved. And we have ongoing work of trying to solve some of them, but obviously it remains to be a problem in practice. And one of the things is that with this tool we're building there, we now have put ourselves actually on the critical path of a real world project, right? Because in the future, WebAssembly, new features for WebAssembly will depend on our tool to be standardized. So this puts extra pressure on this project that may not exist in other similar situations. Yeah, that's all I had. Thank you very much.
Okay, thank you.